Let's take a look at a new example. In 1979, a typical microcomputer contained 29,000 transistors. In 1993, a typical microcomputer contained 3.1 million transistors. Assuming exponential growth, find a model for n, the number of transistors in millions in a typical microcomputer, is a function of t, the number of years after 1979. So we want to write a model in millions for the number of transistors as a function of number of years after. So again, elapsed time as usual. Now I circled in millions because notice that our initial value is in thousands, but then our second value is in millions. So we've got to convert this to millions, and that's what you see down here. So 29,000 converted to millions. This is our conversion factor. A million is 1,000 thousands. Feel free to check me on that. And then you do this computation and you get 0.029 million. So our 2 points are 0, that's a 0, 0.029, and 1993. And 1993 is 14 years. (14) 3.1. So if we're going to use the model for an exponential function passing through 2 points, one way to write that is as follows. So n, you can, one way, now it doesn't actually represent this, but you can think of this as a sub new over a sub old. Now n is actually supposed to represent whatever the n value is that we've gone out, but you can think of this as new and old. And so that would be, for our model, would be 0.029, and this is 3.1 divided by 0.029 again, raised to the t over 14. So n is 14 here. And so that's our model right there. Okay, so there's our model. Now notice we didn't actually explicitly get the growth factor here. I left it in this simplified form, and that's okay. If we need the growth factor, let's just write out what it would be. It would be 3.1 over 0.029 raised to the 1/14th. Again, no variable, no t there. That would be the growth factor. Okay. Now, in this next slide, well, here's the shortcut, okay? So just like we had with linear functions, where we talked about writing the equation of a linear function passing through 2 points, and we used the point slope form of a line and did it that way, and then shortly thereafter we introduced the idea of linear regression, and I said, hey, well, you can also do the linear regression method. Well, you can do the same thing with exponential functions. So you have an exponential regression function in your calculator, and it pretty much has the exact same application as the linear regression function did. So in later units, we will talk about how to use exponential regression for lots of data points, but we can also use it as a shortcut to find the linear function passing through 2 given points in exactly the same way as we did for linear functions. And so that's nice, and it's shorter, to be honest. So let's talk about how to do that. As you can see here, the first thing that we do is we enter the data in the stat editor. So you enter your time in L1 and your function values, your data values in L2. And then we choose exponential regression. So I'll just do it down here. Let me clear everything. So L1 will be 0 and 14. And L2 is 0.029 and 3.1. Then we exit, and to get the function, we go to Stat, Calc, and exponential regression is, I believe it's number 10 or 0. So if you just hit 0 when you do this, then it'll automatically bring up exponential regression. And on my calculator, I have to tell it where to pull the data from. I'm going to save this as Y1, and then I hit enter, and there's my function. So there's my growth factor, which ostensibly is the same value as what we had talked about earlier, and it will be. But so there's my function. 0.029, and the growth factor is 1.396 raised to the t. All right, so I will probably use exponential regression a lot, just simply because it is easier. I'll still use the other formula, but as you can see here, we have two approaches, and they both give us the same model. So this is just lining up both methods. Okay, so let's actually use our model. So let's find, first of all, the growth rate R expressed as a percentage. Now here is where one reason why the exponential regression method is better. It more easily allows me to identify what the growth rate is. So I see that B is that value, and the growth rate is just going to be the decimal portion of this. Now, one annoying thing that happens is as soon as you type anything in here, this screen is going to go away. So if I want to do 1 minus b, right? But if I try to do that, oh, and it didn't happen. Well, actually, that's good. On my actual physical calculator, this happens, but I guess in the emulator that doesn't. But nevertheless, let me show you what I was going to show you anyway. I want to use this whole number, this b number here. So this is actually already in the calculator, and I can call it up, and I want to show you where it is. So if you go to vars statistics, which is number 5, and then equation, then you can call up any part of the equation that you need. So if I just want the b, then that b right there is that 1.39. Now don't use the alpha b for this, because this is a preset value that the calculator has found. So this is different than what I was doing in the previous video. But I want to subtract 1 from that, multiply by 100, and there we have it, 39.61%. That's my growth rate. All right, so at this rate, how many months does it take to double the number of transistors in a typical computer? Let me go back for a second because I want to point something out. This model is in years. This model is in years. And this question says, how many months does it take? Just to give you an idea of how fast this development has taken place, we had a monthly or a yearly model, but we're actually doubling and fast enough that months is probably a more reasonable measure. Okay, but so we want to find the doubling time. My model is already here. I want to double 0.029, so I'm going to multiply that by 2. And then let's go to the table and see about how long we need to think about this. So 0.058 is the number I'm trying to get to, and I've actually already exceeded it. My table set was set kind of high already, so I need to go back. Let's just go to 0. So 0 is 0.029, and then when I get to 0.058, that actually happens like around year 2, right? So that tells me that my window doesn't really need to be any bigger than, say, 3. And then we'll do zoom fit. And then we'll do calc intersect once we get our picture. And our answer is 2.077, so that's 2.08 years. But remember, this is in months, so we need to multiply that by 12. So let's estimate this. 2.08 times 12, 24.96 months. Okay. Part C. Predict the number of transistors in a typical microcomputer in the year 2001. So this is just going to be a calc or a vars, y-vars question. So we'll go to vars, y-vars function, y1. And 2001, this is the way I like to do it, except now I've forgotten when we started the model. When did we start this model? 1979. And 44.75 million. Okay. Let's ask some more questions about this. According to this model that we just found, how much does the number of transistors in a typical microcomputer increase each month? Okay, now I want to make sure that you understand what this question is asking. So when it says by how much does it increase, this is asking for a month, and this is monthly. So this is asking for a monthly growth rate in percentage. Okay. So the procedure here is we're going to get our annual factor. We're going to convert that to a monthly factor. And then we'll convert that to a monthly rate. Okay. So our annual factor, it's all this stuff in here. Now we actually found this using exponential regression, so we kind of have a leg up on this. But our annual factor is 3.1 over 0.029 to the 1/14th. So that's B. Okay, that is B right there. But look, why don't we do this the easier way since we have the data here? You know, I've got that value. I just need to call it up. So I'll go to, if you remember how I did this, I'll go to vars, statistics, equation, select B, and that is the same number right there. Now I want to raise this. What do I want to raise this to? So I'm going from annual to monthly. So I'm going to raise it to 1, actually let me put this in parentheses, to a 1/12th power. Not to the 12th, but to the 1/12th, because we're going from a larger to a smaller unit. And that right there is my monthly growth factor. So I need to convert that to a rate, so I subtract 1 from it and multiply by 100. And that's my monthly growth rate, let's call it 2.82%. And here's a little bit more in detail about that. Okay, I think that's about all the time for this video. We will come back and talk about this bacteria question in the next lecture.